I am Revathi, Assistant Professor, Department of EEE, SNS College of Engineering. In this lecture series video of electron devices and circuits, today's topic is oscillators. So we have already discussed about the amplifiers, feedback amplifiers, and differential amplifiers. So that the improved version of an electronic devices consists of an oscillator, the improved version of an amplifier. We will explore the working principle of the oscillator. Generally speaking, the oscillator produces sinusoidal and other waveforms, beginning with a detailed circuit analysis of an oscillator. We will proceed to discuss the conditions and frequency of oscillation. Following this, the different types of oscillators: tuned oscillator, Hartley oscillator, Colpitts oscillator, Clap oscillators, phase shift oscillator, crystal oscillators, and Weinbridge oscillators. So, an oscillator is an electronic system. It comprises active and passive circuits elements, and sinusoidal produces a repetitive waveform at the output without the application of a direct external input signal to the circuit. It converts the DC power from the source to AC power in the load. A rectifier circuit converts AC to DC power, but an oscillator converts DC noise signal power to its AC equivalents. The general form of a harmonic oscillator is an electronic amplifier with the output attached to a narrow band electronic filters and the output of the filter attached to the input of an amplifier. In this chapter, in this video, the oscillator analysis is done in two methods. First, by general analysis, considering all other circuits are the special form of common generalized circuit, and second, using the individual circuit KVL analysis, which is Kirchhoff's voltage law, where the schematic block diagram showing the difference between an amplifier and an oscillator. In an amplifier, input is given to the amplifier, which is biased supply is applied to an amplifier, and the output is gained. Whereas in an oscillator, there is no need of input, where the biasing supply is given and the output is gained in an oscillator. Oscillators are classified based on the types of the output waveform. If the generated waveform is sinusoidal or close to sinusoidal with a certain frequency, then the oscillator is said to be a sinusoidal oscillator. If the output waveform is non-sinusoidal, which refers to square sawtooth waveform, the oscillator is said to be a relaxation oscillator. An oscillator has a positive feedback with the loop gain infinite feedback type sinusoidal oscillators can be classified as indicator capacitors and RC resistance capacitor oscillators. Different types of oscillators and then frequency ranges. Audio frequency oscillator, which is 20 Hz to 20 kHz. Radio frequency oscillator, which is 20 kHz to 30 MHz. Very high frequency oscillator, 30 MHz to 300 MHz. Ultra high frequency oscillator, 300 MHz to 3 GHz. Microwave oscillator, 3 GHz to 30 GHz. Where millimeter wave oscillator is 30 GHz to 300 GHz. Where Hartley oscillators contains two indicators and one capacitor as shown. Inductance, capacitance. Schematic value, we got the condition for oscillation considering Rn is small. Where Colpitts oscillator consists two capacitance and one inductance. X1 and X2 are capacitance, X3 is inductance, Z1 and Z2 are capacitance, C1 and C2 are capacitance, and Z3 is an inductor of a inductance L. Where phase shift oscillator, the circuit diagram of a phase shift oscillator with three pairs of RC combinations is shown. The equivalent circuit representation of phase shift oscillators by applying KVL is in the circuits. We have the mesh analysis. Crystal oscillators is most commonly used oscillators with high frequency stability. They are used for laboratory experiments, communication circuits, and biometrical instruments. There are usually fixed frequency oscillators where stability and accuracy are the primary considerations. In order to design a stable and accurate LC oscillators for the upper HF and higher frequency, It is absolutely necessary to have a crystal control. Hence, the reason for crystal oscillators are oscillators where the primary frequency determining element in a quartz crystal. Because of the inherent characteristics of a quartz crystal, the crystal oscillator may be held to extreme accuracy of frequency, stability, temperature. Compensation may be applied to crystal oscillators to improve thermal stability of the crystal oscillator. Where the applications are common elements of almost all electronic circuits. There are oscillations build up for zero when power is first applied. Oscillators are used to stable frequency. Computer perhaps counters, timer, digital multimeters, and numerous other applications. Which of the following is not an example of non-sinusoidal oscillator? Which of the following is not an LC oscillator? The sinusoidal oscillator is also called as which type of oscillator is used in timing elements? Thank you.